Hello, differential equations. Actually, hold on. Hello and welcome back to differential equations, section 4.1 on first order systems of differential equations. There we go, much better, right? So, we are going to talk about systems of differential equations, and we're going to stick with systems in chapter 4. Not too much work here, but there are systems that are coupled with there are systems of coupled differential equations, which is what we are going to discuss in the next two sections at least. And let's take a look at a few examples and the need for these types of equations. So we're going to start by understanding that certain concepts in the world will have multiple differential equations that are working together to give us the solution. A perfect example would be what Numberphile did for mapping the virus. So if you go and look that up, you will have differential equations, the two, differential equations that are coupled. Now, there is a weather model that would contain 20-something differential equations that are coupled and so on. So, if you have a single system, with a spring and a mass, we've seen that your displacement x, was measured with mx double prime. Let's not use the dash pot, so there will be no c, plus kx equals to some f of time, So there was the system, and I did not put the dash pot in, so therefore there is no c. And that was, I'll write it over here in block, one equation and one unknown function, which was x of t, which is the position of the object in time. So this equation was what we used in chapter 3, as a second order differential equation, and then we made it spicier when we had the dash bar and so on with a c and dampening and all of that stuff. We can make it a little bit more interesting, but that was it for chapter 3. Now we're going to chapter 4, and for mechanical systems I'm going to have two of these masses, and they are attached like this. So there will be the displacement x, and then there is also displacement y, and they are both functions of time. So if you are to, I hope in physics you learned about free body diagrams and stuff like that. I just hope, So the free body diagrams for each one of these masses, this one, mass 1, will have two forces acting on it. So we have a K1x, which is just the spring constant, which is the spring constant of the first spring. This is K1 spring and K2 spring, So the first, they don't have to have the same stiffness. If the springs had the same stiffness, then you would just use K for the whole problem. But one spring might be stiffer than the other, depending on mechanical need. So you have K1x impacting from one side, and from the other side there is the other spring, which is K2. But now, if you take a look at the location in which this can move, right? It is actually this way. This location is y minus x because you have y and then minus x, right, for this one. So that's y minus x. Over here we'll have y minus x for this one. And for the M2, if you look what we have, we're going to have only K2y minus x on the left, because that's the spring constant. And on the other side, you might have some f of t, right, which is bothering. I did not write that here. I should have, right, because you are impacting it with f of t in chapter 3, so we can use our undetermined coefficients and variational parameters and have those wonderful 40-minute problems where I make 50 mistakes. So we separate the two systems. Now they're clearly coupled through this, right, because this is where they attach. But we see that we can write two separate equations for these systems, and we can. These forces are pushing in opposite, right, directions. So technically, this side over here is behaving as a function that it's affecting the first one. So your differential equation model for the top would be the good old m1 x double prime plus k1 x. So that's the system, right? And the function that bothers it, right, would be given by k2 y minus x. I hope that makes sense. So this is the f of, I don't want to write f of t because I don't want you confusing it with this one. This is the function which bothers the top one. So it's not homogeneous, it's bothered by a function, and that function is obviously coming from the second mass. Now the second equation is going to be m2, whatever the mass of the second one is, y double prime plus k2 y minus x. So now you see that k2 obviously depends also on x, so we have that, and that is equal to f of t. So these are mathematical models that we get to write when we have these systems attached to each other. So now we notice that we have the derivatives and we have regular f of t functions, right? So what we like to do in this case, right, when we have a system of equations, is we like to write our derivatives on one side and all of the functions on the other. There we go. So this would be mathematical model which we are using to describe this situation. So now if these masses and spring constants and f of t are given by something, right, you can just plug those values in and obtain what we would call the system. Now the chapter is dealing with how to solve these systems, so don't panic about solving it now. We are only learning how to derive the system, why do we need the system, and that cool stuff. So say m1 is equal to, I don't know, 3 kilograms, m2 is equal to 9 kilograms, K1 is equal to 0.6 newtons per meter, and K2 is given as, I don't know, 3.5 newton per meters, and the f of t, right, which is the function that bothers everything at the end, right, is going to be given by 3 cosine of, I don't know, 4t, whatever. So what you would do is you would just plug those in, right? You have your M1, so that's going to be 3x double prime is equal to negative K1, negative 0.6x, plus 3.5 y minus x, right, for the top equation, and the one on the bottom is 9y double prime is equal to negative 3.5 y minus x plus, and we have this 3 cosine 4t. Now, these equations can be simplified just a little bit, right? And you get your 3x double prime is equal to negative 6, 3.5, that's 2.9, right? No, we have to add both the negative. So 4.1. So negative 4.1x plus 3.5y. So that's the top equation. And the bottom one, 9y double prime, is equal to negative 3.5x plus 3.5y plus 3 cosine 4t. And here is your system. Now, again, we're not solving it now. We are learning how to take a system, right, a problem, a situation, physical situation, and write it as a differential equation so that we can solve it. So here we go, one more time, right? We have two masses that are attached to each other using this spring in the middle. Now, the first one is also attached with a spring. So what we do is we separate these into what we call free body diagrams, and we take a look at their forces. Because the forces are only acting in the x direction, right, from the left and the right, we only need to make sure that those forces are adding to zero so that we can have equilibrium. Now, obviously, you put this in motion and all of that kind of stuff, you can do more with it, but right now it's the simplest case. So now what we do is we also bother this one over here, right, either way, with f of t at the end. So what we have is these springs have different stiffness. They could have the same, right, but they have different stiffness. So now when I either stretch or push or punch or do something with the M2, because M2 is connected to M1, they both going to start oscillating, and we would like to know where those positions are for each one of the masses at all time. So we set up two free body diagrams. We write our basic equations, but in terms of the new variables, keeping in mind that the distance, right, for the two objects is y minus x, the displacement, and we just plow through equations. You have seen your good old, again, no c term because I didn't put any dash pots in. This is the cheapest possible case. So we have our second derivative and our original function, and x prime and y prime are missing because of because no c, right? And there you go, right? You have those, and now we just do a little bit of arithmetic here, and if we do have numbers, we plug them in to actually obtain the system. So that's the mechanical, right, engineering, something that you guys will do a lot. Now we can also have electrical engineering. Now our last example, right, that we had for electrical engineering had a single, I see something. Oh, I flipped the signs. Okay, thank you. I see the chat now. Yep. Flip the signs. That's positive for x and negative for y. Yes. Good. Thank you. All right. So for electrical engineering, right, in chapter 3, all we had was a source, and then you had maybe a resistor, then you had the inductor, then you had the capacitor, right, the switch. So it was all one loop, one circuit, right? That was chapter 3. But now in chapter 4, for electrical circuits, we can have multiple loops, and each loop will be adding a differential equation to the system. So I can have some source, right, for voltage. Then we can have, let's say, a resistor, and here is going to be a node. Then we can have a capacitor here, right? We can also, I can put a switch. We don't have to put a switch. So, when you charge the capacitor, you put this switch on, it will, whatever. Here is another resistor, let's say. It's terrible. So put the capacitor there, go here, put another resistor here, and then connect all of these on the bottom. I'm not going to I could have put a switch here, but whatever. So, we can have R1, R2, L, and C, because we only have one of each, so I'm just going to call them L and C. And see, this circuit, when you turn it on, it will charge this capacitor here. This resistor here is technically a resistor that is some kind of device. It can be a LED, like a little light. And then this will, the capacitor will store the energy, and once you turn the system on, there's a switch there that can be open or closed, whatever. So when you turn the circuit on, it will light up the LED, and it will also charge the capacitor here, right? And as you when you let the switch go, when you open the switch, right? When you open the switch, this light will continue to shine because it has two storage devices for energy, right? So the LED would still shine for some amount of time, and that is obviously determined by the how strong, right? In quotation marks, how strong these two are. Okay, cool. So that's a basic circuit, and we have our Kirchhoff laws. If you remember that the voltage drops are given by L di dt Ri and 1 over C times Q, right? We can write our loops going through. For those of you who did not have circuits and you didn't take enough physics yet, obviously writing these loops would be a little bit more difficult, and I actually have to teach that on the side. Because Kirchhoff laws, you just follow, there are two laws that you follow. Each one of these branches will have its own current going. So this is a snapshot in time. So current 1, current 2, and we can put this way current 3, and that will just flow through the circuit. So now you have two loops, and you have a node, and you have three currents. Now, if you want to do detail analysis, now we can only focus on one of these currents, right? So current across the capacitor here, because this capacitor will be powering this device over here once the circuit is shut off. So we can only focus on I3. So I can just call that one capital I, because that would be the only circuit that I am actually interested in. And if you take a look at that, right, that current is the only current that it's coming in from the source is this one, and this much is going to go away to power the resistor while capacitor is charging. So clearly I is equal to I2 minus I1, which are I1 minus I1 minus I2, because that's what's the remaining current. The sum of currents in each one of these nodes has to be equal to 0. So technically you have one pouring in and two pouring out of the node, right? So there is a current coming in, that's I1, and then there are two going out. So I1 is I2 plus I3, therefore I3, which is our I for the problem, is I1 minus I2. So you can now write your circuit in terms of the charges and currents, and once you differentiate it, you will get differential equations. And now you have two loops and so on. Again, this gets a little bit complicated for all of you who never had circuits before, who never had, right? We are outlining what is happening here. We're not solving this particular problem. We're going to learn how to solve this problem. So those of you who are electrical engineers, you can use the method to solve your circuit problems in that class. But over here, again, since not all of you are electrical engineering, I'm not going to go into details of how all of this works. But as I said, for each loop, right, we are using the node to come up with a current, and then we are going to do all of these all of these both of these loops will give once and each. So there is, as I said, there is a way too much circuits and detailed electrical engineering that you need to learn prior to, right? It's not as simple as those springs and masses, because for spring and mass you just say, okay, we will just add the forces from left and right, and just, that's it. Over here you have to learn Ohm's law, Kirchhoff's laws, you have to know all three voltage drops, you need to know which way they go, and so on. So it's way more difficult than what we have for. But I just at least wanted to show that mechanical systems would have systems of equations. Electrical circuits will have systems of equations. You can do mixture problems for those of you who are chemistry and biology nerds, right? So we are, dealing all of these, we're dealing with all of these issues, as I said. All right. So now, as I said, for the rest of the class, right, for the rest of this lecture, those of you who are mechanical engineering, you should focus and learn everything about those springs and masses and so on, because that is literally going to be your life for the rest of your career. And those of you who are electrical engineering, computer engineering, and so on, you are focusing on circuits. And as I said, the best way to practice this, obviously, will be to open up your circuits textbook and take a circuit from the circuit textbook and grind through, because you already know how to set up Kirchhoff laws. So electrical engineering students, you know what the Kirchhoff laws are, you know how to go around the loop and set them up. I gave you the voltage drops. So for R over here, you have it here, you write it in terms of charges, you differentiate it just like we had it in our 3.7, I believe, or whatever, and you will have two equations that would be coupled. Now, what we are focusing on actually are, unfortunately, those boring problems where you just have X and Y and an independent variable T, and you just plow through the procedure, right? So unfortunately, that is what mathematics boils down to in today's age, right? So now that we, made the argument that we need to know how to solve these systems, we are just going to now ignore all of the beauty of physics and application and just go into the most boring and dull thing, which is, look at what I can, I can shovel these x's and y's and t's around. So let's talk about first order systems. So first order system would be given as, it's called a first order system because you are going to have two equations which, when you merge them together, you are going to get a single second derivative differential equations, right? So it's a little bit convoluted until you see the full example, but we are going to say that what we've seen so far, x1 is equal to some function f1 of t x1, x2, x1 prime, and I kind of don't want to use 1s and 2s, but because we used x and y, but then you can stretch this as far as you want with numbers as indexes. And the second function, which would be equivalent to our y from before, would be f of 2. I'm trying to keep this consistent with the book, and it's terrible. So we have the same functions involved, as you can see. What's different is obviously this is x double prime and the y double prime, right? And then they would have a different functions of the same components of the same players, right? Let me just give you a quick analogy to stuff that you know from before. I will erase it, obviously. Remember how you guys had 3x plus 2y equals to 7 and 6x minus y equals to 9, right? So these were your two equations. So you see that both equations, even though this is a system and they're paired, both of them had the same variables, right? And when you solve the system, you get x comma y, right? If the system can be solved, you get x comma y. So that's the idea. Now, instead of having only x and y as a variable, you have t, which is independent variable x from before. And then you have first function, second function. So this could be your x and a y. And then your x prime and your y prime if you're having those problems. Now, we are going to have them as x, y, and y prime, but in theory, we like to put these coefficients because you don't need to have only two equations. What if you have 27 equations and in the English alphabet you only have 26 letters, right? So instead of running through all of the letters, x, y, z, and then w, and then u and v, and then, right, you keep adding letters, eventually you're gonna hit to have two t's and have, multiple x's and so on, and it's bad. So for theory, we like to put the values, like values of x1, x2, x3 as indexes to denote different functions. But for our purpose today, we will be looking at this as x double prime is equal to f of t, x, y, x prime, y prime. And notice that these are first derivatives, right? And then y double prime is the different function, g, of t, x, y, x prime, y prime. So this is actually what we need for today, because these are just first order systems and we don't care, right, that you could have 27 functions all coupled and then you would need a 27th letter. You can always, if you ever need a 27th letter, use a Serbian letter sh. There you go. This is sh. Okay, it's a good letter for you to learn, and then use that one as extra variable should you need to. Anyway, so now we would like to figure out how to deal with these situations. So from here, I just want to write, the equation that we can combine all of this into the nth derivative is equal to some kind of a function of the independent variable t. Then you have x, x prime, x double prime, all the way to x n minus 1. So they will actually combine right, into something like that, and then, right, we can introduce the substitution where you say that x1 prime is equal to x2, and then x2 prime, x2 prime, there we go, is x3, which is the, right, so you can put the systems together into a single equation, or you can take a single equation and break it into systems. So it depends on what you need, right, as you are doing the, I mean, we'll do examples, obviously, so you'll see all of this mess. So x prime of n minus 1, which is, you know, the nth function, is x to the n, and finally x to the n prime will be f of t x1, x2, dot, 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 all the way to xn. I understand this means nothing for now until you see the example, but again, we want to see equations to compress into one equation, or, you know, to have one equation break over the systems. It depends on the situation what we need, and obviously we'll see all of that as we go along. Now, obviously, one of the best examples that we can follow, you know, to start this off, is to see, you know, this work on the stuff that we already know. So we're going to take a look at a very basic system where you have your x prime equals to, let's say, y, and your y prime is equal to 2x plus y. All right? So that's a system, right? You can always denote the system using this curly bracket to kind of, you know, clunk it together. And if you pay attention over here, look what happened. You took the derivative of one variable and you set it equal to the second variable. These variables are functions. Your independent variable is t. All of your x's and y's are functions of t, right? So this first line is actually telling you that over here you can say that y prime is equal to x double prime. You are differentiating everything in terms of time. Now, why would you do that? Because look, you have a y prime right there. So now you're going to plug in. And once you plug that in, you will have x double prime is equal to 2x plus, and this y is x prime from the first equation. So what we did is we took the system of two equations and we used the substitution to combine it into a single equation of the higher derivative, but it only has one variable. And that one we can solve using chapter 3. So that's what this mess over here is all about, right? That's what the mess is all about. I take this equation here, I find the derivative, which gives me this equation over here, and now I can just plug in and replace. I replace, instead of y prime, I have my x double prime, and instead of my y over here, I have x prime because y is x prime. All right, so just, you know, find all of the pieces and plug them in where they belong. Now, once we have that, we are done. Now, remember how that mechanical problem and electrical problem would have it the same? There was also an additional plus, whatever was 4 cosine 9t or 3t, whatever, right? They will be floating about as well if we had it. Now, this is the most basic example you can possibly think of, so we don't have it, but we could have, and then you would just have undetermined coefficients to worry about as well. All right, so now what do I get? X double prime minus x prime minus 2x equal to 0. Now this one you can factor, right? You have your r squared minus r minus 2 equal to 0. So that's going to be r minus 2, r plus 1 in my book. So r is 2, r is negative 1, and this is where 3.1 kicks in, right? All of this is 3.1 to solve. So today we're learning how to convert so that we can use what we know from before to solve the problem easily. So what I learned from here is that my x of t is c1e to the 2t plus c2e to the negative t. Now, let me write this in blood. We need y of t as well. All right? Yeah, don't just say, yeah, got it, got the x and walk away. There is a y to find, and y is x prime. In this case, cheap as hell, right? So, y equals x prime. So, what's my y of t? My y of t is simply the derivative that I have up there. That's going to be 2c1 e to the 2t minus c2e to the minus t. And these two together are my solution. So solution is given by x of t equals c1 e to the 2t plus c2 e to the negative t, and y of t equals 2c1 e to the 2t minus c2e to the minus t. And that would be our solution to the system. Right? So our job is to figure out, right, this system here and figure out the system and combine it into the single second order. Now, what happens if you have higher derivatives? Well, they are going to combine to higher orders, which is where our 3.2 kicks in. As long as you can factor and get those r's and repeated and complex and all of that stuff, you should be able to plow through calculations. So the idea is to somehow combine all of these cases. So I just want to go and find another problem in the homework to solve, and then we're going to work more on how to break this apart, right? Because this is more of a putting them together. So let's see, and I would like something with the driving term, but I don't have it. Yeah. Let's do something with initial conditions. Problem 20 is one of them. X prime is 10y, and y prime is a negative 10x, and x of 0 is 3, and y of 0 is 4. So that's our life now. So we note that we have a y and a y prime. So I can just solve for y, differentiate and plug in. But I can also do it the other way. I can solve for x, differentiate and plug it here. So it doesn't really matter which way you do it. It's just, solve one of them and then go from there. So my y is equal to x prime over 10. From there, my y prime is x double prime over 10. Plug in. So x double prime over 10, which is the y prime, is equal to negative 10x. So I'm going to multiply the whole equation by 10 and get x double prime plus 100x equal to 0. That's it. So instead of y prime, I put in x double prime. I keep the x because I want all of them to be in terms of the same function x of t. And now I need to solve this. This is r squared plus 100 equal to 0. Hey, that's complex, right? We got a 10i over here. So that's r equals plus minus 10i. Because it's a plus. If this was a minus, it would just be 10 in that case. But when you move 100 to the other side, it becomes minus 100. Square root of minus 100 is 10i. So what are my x solutions? My x solutions, x of t, right, is equal to, there is no a term over here, therefore there will be no e. We'll just have a cosine sine solution. So this would be c1 cosine 10t plus c2 sine 10t. So that's our life. And we can quickly come up with what y is, because we know that y is x prime over 10. So the derivative of cosine is negative sine, and then there is 10 in front. If I just write the solution, would your brain explode? There is a 10 that jumps out, and then it's over 10, and it's negative, and then there is a c1. So we only get 10 negative c, right? I hope that makes sense. Then the derivative of sine is cosine, so there will be 10 c2 10 cosine 10t, but then I have to divide it by I have to divide it by 10 because it needs to be divided by 10. So I'm just getting c2 cosine 10t. And that's the solution. But we're not done. They want us to use x of 0 is 3. And y of 0 is 4, I believe. So what we have is now we need to plug these values in and see what comes out on the other end. So for x, it was going to be 3 is equal to c1 plus c2 is 0. Perfect. So c1 equals 3. How about I actually write it? Cosine of 0 plus c2 sine of 0. So from there, c1 is 3. There we go, much better. And then the second equation, 4 equals negative c1 sine of 0 plus c2 cosine of 0. From there we get that the c2 is equal to 4. So I have my solution, right? It's x of t is equal to 3 cosine 10t plus 4 sine 10t, and y of t is negative 3 sine 10t plus 4 cosine 10t. Yeah, I'm just hoping you guys are watching this like on a central, like a TV system or somewhere where everyone is forced to listen to this stuff, including your neighbors, like max volume, blasting to the entire neighborhood, right? Not like on the headphones hidden in darkness somewhere. It's like right in the living room on the TV, right? So everyone can enjoy this. All right, so we got this system solved. And again, these systems could be mechanical, could be electrical, could be mixing stuff for chemistry and bio, right? Because they're all about alchemy in labs and stuff. So, you know, mixing magic potions called medications and vaccines and stuff. So, anyway. So, believe it or not, that's it, right? That's it. But is there a way for us to break this into couple of functions if we need the system? Because sometimes, right, you can break the system into multiple equations and then go from there. We will see later that we can use matrices and stuff from linear algebra to solve this system. So, is there a way for me to somehow get a system out of an equation? Because that is also the skill that you guys are going to need later. You're learning it now, but it will be needed later because later I can use matrix. So let's say you have y triple prime plus 9y double prime. Actually, I have to, let me add some title above. So we're still going to have the same problem. I just want to leave some space for title. Converting into a system. So, I don't know, y triple prime plus 9 double prime plus, 3y, 3y prime minus, 6y equals to e to the 3t. Whatever. You literally put whatever you want, right? Because it's just the procedure of how to create a system out of the single equation, right? So now I have this third degree equation. I can't factor it, and I hope I can't factor this one. So because I can't factor and it's so nasty, I'm going to go and try and solve this in some other way. And that other way would be to use matrices and things later on, and even numerical, right? Numerics and so on. So what should I do? Well, the way we started working with these things is we are going to remember, right, that all of this is equal to some function f of, I kind of hate using lowercase f. I mean, that's what they used in a book when I looked at it earlier. We like to use capital F in most of the cases, right, for the implicit forms. But yeah, such is life. So this is t, y double prime, y triple prime, y prime, y double prime, y triple prime in this case, and that is going to be equal to, and now we have all of this mess. Now we are going to write this in the opposite order than what we have over there. So now we're going to move everything to the other side, so it becomes 6y minus 3y prime minus 9y double prime minus y triple prime. and then we'll have plus e to the 3t because that was already there. So all of that, we're going to call this as some implicit function, right? It will be equal to 0, but we don't need to worry about it. So that's some kind of our implicit function now. And the trick is to start introducing variables now that will propagate through the problem, right? And this is where 1, 2, 3 comes in because, right, we have 3 derivatives, so we only need 3 variables in this case. But can you have 27? Yeah, and then you don't have enough letters in the alphabet. So I'm going to say that my y1 new function that I'm using now is y. Now y2 is going to be y1 prime, and y1 prime is y prime, right, because of the top one. And then y3 is going to be y2 prime, which actually is y1 double prime. I hope that makes sense. All right, so what we can do is we can do the y double prime there, because then I don't have to solve it. Yeah, let's do this. So y3 is going to be y double prime right? And that's going to be our y2 prime. Good. All right. So now we have our system. So I'm going to call, right, these ones are substitutions. So what is my system? Remember, now my new variable functions are y1, y2, and y3. So y1 prime is equal to, what is y1 prime? Look for y1 prime. Where is y1 prime? It's right here. y1 prime is equal to what? To y2. Because they all need to be in terms of these singles, and you have to have derivatives in the front. So what is a y2 prime equal to? Where is my y2 prime? Right here. What is that equal to? Equals to y3, right? And now what is my y3 prime? I didn't solve that one yet. What is a y3 prime? If I differentiate this one, I will get y triple prime, right? In here. Do I have a y triple prime? I do, right? Maybe I should have done that. That might be a little bit confusing part, so let's put it in blue over here. So y triple prime. Well, let's start with steps. Let's do y. So y3 prime is y triple prime, and then solve for y triple prime. So what is y triple prime equal to? Right, y triple prime from there is going to be y triple prime on the left, and everything else stays on the right. So that's 6y minus 3y prime minus 9 y double prime plus e to the 3t. And now this one is y1, this one is y2, and this one is y3. So my y prime 3 is 6y1 minus 3y2 minus 9y3 plus e to the 3t. Woohoo! There it is. Yeah, we need to do another example. I know. Even before you type anything. But what I did is I took a single third degree equation, and broke it into 3 first order equations. Now, again, that's needed for later. You do not get to solve this. To solve this system now, well, you would put them together. And what would they work out to be? They would work out to be your original problem, right? That if you can solve with 3.2, which is more than a second order, right, solutions, then you can't do it at all, right? So the idea is just to learn how to put these, how to take one equation that it's a high order differential equation and break them into the appropriate amount of the first order equations. So I'm going to run through this argument again, then we can do another, let's say, second order and another third or a fourth order, and then call it a day, because in this case we're done, right? So let's go run through this argument again. I have some differential equation given, and I can write that differential equation in its implicit form over here, where I put all of these on one side. Now I start defining new functions, y1, y2, y3. You can go x, y, z, or you can, if the problem didn't start with y, you start with something else, you can do x, y, z functions. I don't care what you're going to use, right? I'm using y1, 2, and 3. It's easy to see that it was a third order, and you actually get 3 in a system. So we start defining that this the function y1 is equal to the original function y. That's the unknown function. I don't know what y is, right? But y1 is equal to y. Then y2 is going to be y1 prime. Now that's equal to, we don't really need this part, but it's good to know that you can differentiate, right, and that it couples back to the original y, because your original problem is only posed in y's. You don't see any y's here, right? You don't see any y's there. But this first equation tells you the relationship between the y and y1. So everything can be traced back to y1, and then everything eventually can be traced back to y, because your original problem is only posted in y's. So we are not using this part here other than to tie your we're not using this part. That's the way. We're not using that part at all in our equations other than to tie it back, right, to the original problem. Because all I need to do is to define that y1 is y, y2 is 1y prime, and y3 is y2 prime. Right? That's all I'm doing. Right? What is the y for? y3 prime. What is the y for? Right? As you go, you are using the stuff in red. This one. Right? This is the key. This is what I'm using. Right? So flies. Perfect. So once I define my functions here in terms of y's, all I need is the y3 prime. And y3 prime is y triple prime. Solve it, because you have the equation for it. Solve it, plug it in, and now you just write the system. Let's take a look at second order. So this was a third order. I thought it was a good example to come up with, because I just made this stuff up in terms of the equation. I didn't use the homework or exercise or anything, but let's take a look at the homework exercise, where you are going to break this apart. Transform the given differential equation or the system into an equivalent system. Okay, cool. So they are giving us a system, and I just want to find a second order system, something that it's okay. How about problem number 3? Could have used problem number 1 as well, or 2, but whatever. So x double prime plus 2x prime plus 26x is equal to 82 cosine 4t. This is some kind of a mechanical system, right? With dash part, right? Because you have a c, your mass is 1, right? Then you have this, and there's your k, right? And there is the function that bothers the system. So we did this in 3.4 or 5 or 6, right? We did this somewhere, maybe 3.6. Yeah, 3.6 had us. So yeah, whatever. You know how to solve this without systems or anything like that. But what I want to do here is I want to break this into a system for later on in life. So what do? Well, first of all, we can just write our f of t, right, as 26x, negative 26x, minus 2x prime, minus x double prime, plus 82 cosine 4t. That's if you solve each first order differential equation, then you can't solve them separately. They're all solved simultaneously. So we are focusing now on two different things in this section. One is how to solve systems by, when you have a system, you push it together into a single equation and solve it. And the other part is when you have a high order equation that you can't factor and solve by what we learned in chapter 3, how to break it into a system so that later, not now, not today, but later, how to use that system to solve the equation that you couldn't solve by chapter 3. So we are now pretending that we don't know how to solve this equation. We are pretending we don't know chapter 3, so we want to break this into a system of two equations because the second derivative, right? We are pretending we don't know, so we can break this apart. That's all we're doing now. And then once we have the system, what we're going to do with the system is later in the course, not now. Okay, so I am writing the implicit form, and now my x1 is going to be my good old x, and x1 prime is going to be, my x2 is going to be x1 prime. So that's what we have, and clearly I need x2 prime. Now x2 prime is x1 double prime, which in turn is x double prime, and x double prime is negative 26x minus 2x prime plus 82 cosine 4t. So usually this line is where you go nuclear. So I'm going to go through it one more time. The first two lines should be clear. You are defining two new functions, function x1 of t and function x2 of t. Why are you defining two? Because your original problem was a second order. The order of the differential equation tells you how many equations you have to have later. So the first two lines we really don't need to talk about. It's this third line here that it's a living nightmare, right? Because now you need the derivative of this, because remember, your system is x1 prime equals 2 and x2 prime equals 2. That's what the system was defined. If I scroll all the way up to the beginning of the lecture, what do we find? Derivatives are equal to the blah blah blah, right? So whether they're first or second or third or whatever derivatives they are. So when I go back to this problem, there we go. When I go back to this problem, I define my new functions and then I just follow what they are. And when I get to x2 prime, x2, I differentiate both sides, which adds a second derivative on x1. That's how I got that. But now, since x1 is equal to x, then it's just x double prime. And I know what the x double prime is equal to from the formula. Just take this and push to the other side. So it's a little bit convoluted, but just, rewind the video a few times and you'll get it. It's not, even if it was rocket science, you sit down and learn it. So what's x1 prime equal to? It's equal to x2. And what is x2 prime equal to? Well, we already have it written here. Again, we're not solving this. We are just breaking it apart, transforming it into a system. You would say, well, why don't you want to solve it? Because I don't need any of this stuff to solve it. I know how to solve this without anything. Again, this is not designed for the second order. This is designed for the third and the fourth and the 100th order when you cannot factor using chapter 3. Remember, in order for you to use chapter 3, it has to be factorable, right? But then I remember Mike asking once, what if I can't factor? Well, welcome to what if you can't factor. If you can't factor, you break it into multiple systems, right? Systems of equations, right? Multiple equations. And then the rest of the book, right? We're not there yet. We're just learning how to transform this mess. All right, let's take a look at, well, they have fourth orders. Chapter problems 5 and 6 are the fourth order. So why not? Let's go with the fourth order. Here, problem 6, whatever. X to the fourth order plus 6y double prime minus 3x prime plus x equals to cosine 3t. So what is this? Well, this is an equation that has 3 loops in it for circuits. It has 3 masses, right, for attached with springs. Could be attached on the other side as well, right? So you can have a mass, a mass, a mass, and then a spring, a spring, a spring, a spring, right? There you go. So it would eventually combine into this one, and then you also act on it. So it's not so this cosine 3t is right there. Actually, you know what? I'm gonna do this. I'm gonna do that, and then instead of this one, I'm just going to do boom. There we go. Perfect. Right. So So you can get these systems. You can get these systems easily. Now our job over here is to convert this into. Our job here is to convert this into what we have as a forward. Why? Because I can't factor this. I can't solve this using what I learned in chapter 3. It's not what you would say nicely factorable, right? So my R method doesn't work. R to the 4 plus 6R squared minus 3R plus 1 equal to 0. I can't do that. And because I can't factor the polynomial, right, I can't solve differential equation using chapter 3. So I have to come up with this new method here of converting my differential equation, right, into a system of 4 differential equations. 4 because of the 4th derivative, right? And so let me actually write it here in blood. Because we have x to the 4, we must use x1, x2, x3, x4. So we must use 4 of these functions for our systems. Now, can these functions be called y, z, w, and v? Yes, they can, right? You can't use x, you can't use t, those are already used up. But if your life would be improved in any way by calling this y, z, w, and v, go ahead, right? But these are all functions of t. Maybe I should write that in, right? How about I write that in? x1 of t, x2 of t, x3 of t, and x4 of t, just to be, as transparent as possible. Cool. So what are my subs? Well, we are always starting the x1 is just x. The good old x. And the next order of business is what is x1 prime. So what is x1 prime? Well, x1 prime is just x prime. Right? Now, I am going to define x2 as x. Actually, I should have written this on the side. I'm just going to put it here in parentheses. x1 prime is x, but we're going to come back to that because I'm defining x2 to be x prime. x2 is going to be x prime. x3 is going to be x double prime, and x4 x triple prime. Let's just start there. Let's start there. I could have defined x5 and x6, and this could be to any order. I don't care. There's your setup for the variables. So variables for functions. So x1 is x, x2 is x prime, x3 is x double prime, x4 is x triple prime. So now that we have that, we can link them back to the other variables, right? So I know that x prime is x1. So from here, I will get that this is also, let's go blue. I'm going to delete this. So this is also equal to x1 prime, right? Because I can differentiate this one, and then I'll just have prime equal prime, right? So what is, let me also write over here what I need. I need x1 prime, x2 prime, x3 prime, and x4 prime. Those are the ones I need. That's what I need. So from this equation here in blue, I found that x1 prime is x2. That's what I found. Now we are going to go to the orange equation. What is x double prime? I hope you see that if you differentiate here, you will get that x double prime is x2 prime. So from the orange equation, I found out that x2 prime is equal to x3. Then I'm going to go to the purple. What is the triple prime? Well, I differentiate this one. You always differentiate one above. What's the triple prime? Triple prime is x3 prime. So from the purple equation, I learned that x3 prime, right? x3 prime is x4. And finally, at the end, let's go soothing green. The next equation is, what is x4 prime? Well, x4 prime is x fourth derivative. Now that is given in the equation above. So I just solve for this guy. And that is going to be negative x plus 3x prime, blah, blah, blah. So negative x plus 3x prime. Actually, you know what? Let me do it here. Negative x plus 3x prime minus 6y minus 6x double prime. Why are these y's up there? Why is there a y here? It's x. What the hell? It's x. They're all x's. Okay, and then plus 3 cosine t. Okay, plus 3 cosine t. So now, for the green equation, I just need to use appropriate variables. My negative x is negative x1. My x prime is x2. So plus 3x2. My x double prime is x3. Oops. Not cubed, x3. And then I just add plus 3 cosine t. Ta-da! I know it's neurotic with all the colors, but that's the answer. So the answer is, for our system, copy, paste, black, there we go, and the box. There we go, done deal. So I started with the fourth system. What, a cosine 3t? What did I write? 3 cosine t? Cosine 3t, yeah. The tablet is being really annoying. I can't focus because it has so much lag. I guess I just installed updates And now it's downloading something again, probably, and it's lagging, and it's very difficult to write. It's very slow responsive. My brain is going like 5,000 times faster than the computer here. It's just, I just can't focus. So, is it cosine 3t? I messed it up here as well. Yeah. It is the same. Again, all we are learning is how to break whatever order, 7th order, 7 equation, 10th order, 10 equations, 2nd order, 2 equations, right? So whatever amount of equations we have, how to break it down into a system. Why do we want that? We want that because if we can't factor a 3rd or a 7th order equation, if we can't factor when we do the R method, right, with the characteristic equation from chapter 3.2, if we can't factor, we can't come up with those roots and those solutions and all of that stuff we learned over there. So we need something else, right? And this is a foundation for something else. So you need to be able to break an equation apart into a couple of other equations, and also to put them all together, right, into a single equation. So that's a backwards procedure. If you have a system, right, because you observed the system, mechanical, electrical, or whatever else, right, you observe the system, and then you want to mush all of those equations into a single equation and hope that it would factor, and hope that you can solve it without, going crazy with something with systems. Let's see if we can find one more example of going the other way, which is, here's the system, put them all together, see what happens on the other end. Yeah, they don't actually have many of those. Yeah, let's just solve one more of them, and none of these have trig or e's. They're all boring polynomials. Whatever. 24, I guess. 24, and we'll call it a day. So x prime is negative y, and y prime is 10x minus 7y. So from the top equation, now we are condensing them, right? This is a system. So we want to mush them together into one equation. Now, when you take two first orders, they're going to combine into a single second order. So from the top, I have that y is equal to negative x prime. Then I differentiate both sides d dt, and I get that the y prime is negative x double prime. And then I just plug in. So instead of y prime, I have negative x double prime equals to 10x minus 7 times, and instead of y, I have negative x prime. So I hope all of these things, made sense for a hot second. And now, negative x double prime minus 7x prime minus 10x equal to 0. multiply everywhere by -1, x double prime plus 7x prime plus 10x equal to 0. And we are in a position to do the characteristic equation and hope for the best. Well, you can do quadratic equation, obviously. If it's not factorable, who cares? There is a procedure for a third and a fourth degree, but there cannot be, there never will be a procedure for the fifth and above. So that's why we have to deal with all of this nonsense. Plus 7r plus 10 equals to 0. This one factors, so r plus 5, r plus 2, to give us -5 and -2. So I have my x of t as c1 e to the -5t plus c2 e to the -2t. That was chapter 3, right? All of this over here is chapter 3.1. That was all there. So the way to convert over here, that is 4.1. That's all. The rest is all chapter 3. All right, cool. So now I have my x, I need y. What's y? Y is -x prime. So what's y of t? Y of t is going to be negative derivative. So -5 c1 e to the -5t plus -2 c2 e to the -2t. And now we can just put both solutions together. So x of t is c1 e to the -5t plus c2 e to the -2t. Y of t is equal to 5c1 e to the -5t minus 2c2 e to the -2t. Ta-da! Solutions. What did you say? You don't believe me? Well, then check it. Plug in both, make sure they work. Right? Would y prime be the same as 10 times x minus 7 times y? Just work out the arithmetic, right? Differentiate this and equal it to 10 times this one minus 7 times that one, and it has to work out. And that's that. The next section is going to be the method of elimination, 4.2. And I think on Wednesday is our review, actually, for midterm. So I think that's good to go. I see something about plus 2cc. I'm not sure what that means. Plus 2cc. I'm not sure what the chat message means. We do have our c's. We did not have initial conditions to compute c's, so we can't do that. Oh, the plus in the solution because it distributes this minus on both. Yeah, sure. Yep. See, if I checked it, I would know it was wrong, but because I didn't check it, luckily I have 10,000 viewers to tell me I'm wrong, on the live stream, which is amazing. Thank you all, like and subscribe. So, yeah, it's just too much of these calculations and stuff. Anyway, Wednesday, we're going to do the midterm review. Watch for the post. I tested office hours, so office hours will be available on Microsoft Teams. So you will join the office hour team if you care, and you can go and figure out. So there will be eventually the system will generate the email for you to click in. Once you open the email, you click on the link and it adds you to the office hours list. And then when I come up online, if you want to use camera, you can. If you don't want to use camera, you don't. But you will be able to, if you're using camera, obviously you can use the microphone as well, right? Then we can communicate. Yeah, office hours are going to be a little bit probably chaotic because, everyone is going to be connecting, but we'll see how that mess works. I tested the Microsoft Teams, worked great, but I only worked with one person, right? I don't know, if 10 of you from different courses show up and I have 40 people, let's say, or 50 people in one instance. There's just no good way to do office hours. I have 5 classes. They're different. They're different levels, from elementary algebra through differential equations. So there's no good way to do office hours. I don't know what else to do other than right? And then you will have to sit through, you as a differential equation, you will have to sit through me explaining slope. And then someone from algebra will have to sit through a 20-minute problem that you guys have. So it's just, there's no good way because the schedules are all over the place. And I am already working way too much in terms of the online nonsense we have, the instruction. I just don't have available hours to say, okay, each class has its own time because everyone else has life. So there's no good time to say, okay, differential equations office hours are at, Wednesdays at 5 p.m. Because if I say Wednesdays at 5 p.m., there's going to be, a couple of you to say, well, I can't. I have other class, I have work, right? So office hours are going to be my regular office hours. And then if we have anything extra, at least I'm posting all these videos and stuff. So you guys can rewind and, go back, and I am writing the exams from this stuff. So hopefully, all of that will work. That's it for today. Wednesday is the review. I'll see you all. Bye. Watch for announcements for the office hours.